So in terms of positive correlation then, so hopefully you've seen a graph a little bit like this from high school maths, and it's a sort of very simple fundamental underlying idea. So the idea x increases, y would also increase, uh, equivalently also as x decreases, so decreases. And the classic example I was sort of mentioning before was if you had something like petrol costs and grocery bills, so cost increase, you would expect bills to increase proportionately to that. Okay, so sometimes you've got to use your sort of imagination a little bit. If you have a real data set, it's unlikely to give you such a sort of perfect correlation. But the basic idea with positive correlation is that as one variable increases, the one decreases. This is again, it's a sort of relatively straightforward fundamental principle from high school level maths, but on occasion you might need complicated regression techniques to decide whether this is indeed the case. We'll show you some examples later in the lecture later in the lecture course rather, where this correlations exist, but they're not as perfect as this. So to be as precise as possible, correlation is not causation, but loosely speaking, if two variables x and y are negatively correlated, then as x increases, y decreases, equivalently as x decreases, y increases. Now the reason why this idea might be important is that if you were trying to make the variable y as large as possible, this would indicate that you should make the variable x as small as possible. Equivalently, if you wanted to make the variable y as small as possible, you should make x as large as possible. Okay, so the idea of this negative correlation is it's a restatement of basic principles that you'll hopefully seen before in high school maths. Now, one classic example of this might be something like fuel costs and the profits made by a transport firm. So you might naturally expect then, if x is the fuel cost and y is the profit from the transport firm, as the fuel cost increases, the profits made by the transport firm decrease because they've got to spend more money on putting money in the trucks, for instance. Okay, so lots and lots of examples in finance and economics of negative correlation. And what I wanted to emphasize here is this is a sort of central tenet of regression type models, but there's a basic picture underlying it and basic principles from high school. So this is a sort of cartoon version of negative correlation, and I'm sure you'll have seen little graphs like this before from high school maths. The idea is that increases, y decreases, equivalently decreases, increases. So as I said before, if you wanted to make y as large as possible, you would try and decrease x. Make y as small as possible, you would want to increase x. Okay, so you can hopefully see then lots and lots of possible scenarios that might reflect this graph in finance and economics. So my example earlier is made by the as the cost increase of the transport firm if fuel suddenly becomes cheaper, you'd expect the transport company to suddenly start being able to increase their profits. Okay, so it's a sort of very simple concept, very simple, absurdly simple in high school maths, but this still has relevance for the regression models that we talk about on this course. Okay, it's just that examples that you see in the course will be less in this graph. But alongside this then, one natural pattern you might expect to find is zero correlation. So the same disclaimer as before, correlation is not the same as causation, but loosely speaking, if x and y are uncorrelated, a change in x does not affect the change in the value of y. So if you plotted two variables x and y that are uncorrelated, you would expect to find this flat line here. Okay, so real data examples. I'm afraid this graph that you've got here won't apply. Actions caused by sample variation, but this is the basic idea. If X and Y are uncorrelated, then if you change, make it bigger or make it go smaller, and have an impact on the value of Y. Okay, and this is although it's a sort of absurdly simple picture, this does have a lot of relevance when it comes to systematic treatment of regression type models and some of the tests that we'll talk about later on in this course. Okay, so at the risk of repeating myself, the basic question remains: if you change X, what happens to Y? Nothing in this case, the zero correlation, but Y would either increase or decrease depending on whether there's a positive or negative. So there is a disclaimer. We'll see some examples of this later on in the course. You may have to use your imagination a bit. Real data sets often produce sort of roughly similar patterns to these graphs, but are liable to be very imperfect. In contrast, what we've just shown you there are sort of the perfect cartoon graphs that you've seen before, sort of high school maths. Now, when you see these sorts of graphs for real, they're imperfect, and their imperfect nature means that you need statistically rigorous regression models to decide which of these three scenarios applies. Statistically rigorous regression methods just binds to real data when the fit isn't perfect. You may also see examples where graphs are curves rather than straight lines. So these are three graphs which are obviously a sort of very extreme case of when everything works perfectly, but the reason I thought it was important to sort of present it like this is that even if you're looking at a complicated regression model, the same basic principles apply as apply to very simple maths that you see at high school. Basic question is there zero correlation? If there's not zero correlation, is there positive correlation or negative correlation? So for the next part of the lecture, I wanted to talk about data presentation. And again, although we're talking about quantitative methods here, which can be quite involved, really I want to emphasize here that the purpose remains communicating information simply and as effectively as possible. In terms of data presentation, is built on, I think it's usually better if there's a sort of graph or a picture you can draw to sort of support and reinforce the concept. And this is my favourite topic in mathematics and in finance. The different ways of presenting data are important, and the sorts of things you might see in reports and especially in the fundamental aim is to communicate information simply and effectively. Graphs and tables are often an effective way of doing that, and I think you're unlikely to be too clever to have to think carefully about how to present data and how to communicate well. Here, the methods covered are stem and leaf plots, tables, frequency and histograms. Now, some of these you're likely to sort of see in a real report, but certainly frequency tables and histograms are so. Again, I would like to try and emphasise the importance of communication here, and I think you can sort of view this lecture material as an extension of other important professional skills, certainly as far as accounting and finance are concerned. So what we're really on about here are simple ways to communicate and display information. Important key skills I think for accounting and finance are general numeracy, that can be separate to mathematics and statistics of course, and probably most importantly attention to detail, which is especially important. And again, I think this is the thing that I have the maturity and the experience to fully appreciate. What you're really doing here when you're looking at these graphs and tables is you're looking at simple, complex or statistical information. be more interesting and more advanced bits that you need an MSc, PhD experience to properly understand. Use these sort of simple tables as a cross-check of the harder and more advanced material. So, appreciate this isn't necessarily, but the main thing I want to emphasise here is if you achieve that. The first thing I wanted to talk about in this lecture are stem and leaf plots. So, if understanding the name of these things is that the stem is the big bit and the leaf is the small bit. And what this is intended to do is an alternative way to write down the whole data so that you keep the original data, you don't lose any of the values in the original data set. You also get some sense of the scale of the data and how it's spread out, both in terms of the entire sample and within little subgroups within that sample. The idea is the big bit is the leftmost digit. Rightmost digits, leaves should be in size order. So you're trying here to get a sense of the spread in the sample, both in terms of the entire thing and how the things are spread out in separate subsections of that sample. This approach is simple. It's trying to give you an overview of the sample and the shape of that sample, giving you an indication of the spread of the data within each subcategory. It does retain the original values. Methods, it does not rely on the class midpoint. Example here, so we've got a stem plot for some scores. Plot for this data would be shown in the table. So it is a little bit of a sort of overly simplistic example, but hopefully you can sort of see there in the table you get some sort of sense of the shape of the data, so an idea of how the thing fits within each category. So if you sort of turn your head to the side, you can hopefully sort of see that this graph is clustering in the 40s and happily more people seem to do well 60 or 7% than 40%. So there is some symmetry in this sample. Now, these things aren't necessarily terribly exciting, but the idea here is just to sort of communicate information simply and effectively, and hopefully you can sort of see that you get more of a sense of what the sample looks like from the stem leaf plot in the table and the raw listing of the data in no particular order at all. We see once you've got a larger data set. Second example here, so suppose you've got the following data on wages recorded in dollars. Here would be that the thing doesn't break down with an arbitrary change of units. Stem is always the big bit, the leaf is the small bit, so the easiest way to present this data would be dollars and the leaf bit to represent. Once you construct the stem and leaf plots, again you get a sense of the shape of the whole sample and a sense of how the data is distributed within each subcategory. So the main point of this is competent and efficient data presentation. Not a very exciting example. See that if you look at the stem and leaf plots in the table compared to the raw listing figures, you do get more information from the stem and leaf plots in the table, and you can get a sort of decent picture of the shape of the distribution of the data from the stem and leaf plot and the larger sample and then fully defined shape